Okay, so we're now going to look at the energy and carbon dioxide consequences of waste, the waste that we produce. So let's imagine that a household makes 20 kilograms of organic waste each week, and that waste is basically, we'll assume it to be cellulose. Then in a year, how much energy is consumed trucking the waste to the landfill, which is 200 kilometers away? How much energy is consumed if we just transport it 20 kilometers to an incinerator, and then how much is consumed if we compost it in the backyard? Well, the answer to this is just zero, because there's no fossil fuels that are consumed there at all. So with 20 kilograms per week times 52 weeks, that gives us a total of 1,040 kilograms, which is 1.04 tons. Now we're given here the energy cost of transportation, 3.2 megajoules per ton kilometer. So we've got our 1.04 tons, so this is for part A. So that's our annual waste. And then our trucking cost of transportation is 3.2 megajoules to ship a ton a kilometer. And we're told we're shipping it to the landfill 200 km away. So this gives, you can cancel the kilometers, cancel the tons, this gives 665.6 megajoules, which is 0.666 gigajoules. Now in part B, we're only trucking at 20 kilometers, so this is just going to be 1/10 of this value. This is just 66.6 megajoules. We've already said in part C the answer is just 0. Oh, but hold on. Before we get to that answer in part C, let's actually note something. This is an energy cost, but there's actually an energy gain associated with incineration, because we're going to make energy at the incinerator. We're going to make quite a bit, actually. So the actual production of energy we get by burning that cellulose, cellulose has an energy intensity of about 13 megajoules per every kilogram. So we've got 1040 kilograms of cellulose over the year, and each kilogram's got about 13 megajoules in it. And about 15% of that can actually get converted to electricity. And so this works out to 1961 megajoules a gain. So the net positive, or the net gain, is just the 1961 megajoules that you get from burning the garbage, and you convert that into electricity, and then the 66 megajoules that, oh, I'm sorry, that's incorrect. No, the actual answer here, if you multiply it, is 2028 megajoules. Then when you subtract the 66, that's when you get the 1961 megajoules. So that's the net. Okay, so there's a gain of about 2 gigajoules minus the tiny cost. You're actually producing energy by shipping it to the incinerator. And once again, in problem C, there's no energy associated with composting in the backyard. Now, how about the carbon dioxide implications of doing this? Well, there's two things to consider. First of all, there's the carbon dioxide that's produced in the trucking, because we're burning diesel fuel, and every kilogram of diesel fuel or petroleum or every gigajoule rather of petroleum that we burn, we get about 68 kilograms of carbon dioxide. That's a number from the text. So when we look at the drive to the landfill, it was 666 megajoules, or 0.6656 gigajoules of petroleum. And we'll use this intensity, this carbon dioxide intensity, that many kilograms of CO2 per gigajoule of petroleum. That gives 45.3 kilograms of carbon dioxide, let's say equivalent, but really just carbon dioxide released into the air. Driving it to 1/10 the distance to the incinerator, it's still going to be 4.53 kilograms of CO2 that's produced in the 20 kilometers of trucking. So clearly, once again, the landfill loses. There's a lot more carbon dioxide produced there. An important consideration, though, is that there's another source of carbon dioxide. We have considered the carbon dioxide in trucking, but the landfill itself, in the landfill, the waste is going to decompose and it's going to make carbon dioxide. Okay, if the carbon in the cellulose is completely oxidized, you're going to make carbon dioxide. However, there's a net of zero because it's just a biomass recycling of carbon dioxide from the atmosphere into the cellulose and then back into the atmosphere. Same thing with the incinerator. There's a net of zero carbon dioxide associated with the decomposition of the waste. Now, this is all assuming that there's no methane that's released. And why is that important? Well, let's have a look. So in the first case, let's look at a plant, and it's going to absorb carbon dioxide from the atmosphere as it grows. Now, let's say it absorbs a ton, just for instance. Now, when that plant rots later, if the carbon is completely oxidized, and if we get that same 1 ton of carbon dioxide released, you could see that the net for the atmosphere is basically zero. And this might happen over a year, it might happen over 50 or 100 years, but it's a fairly short-term cycling of carbon dioxide out of the atmosphere and then back into it, and it doesn't affect the chemistry of the atmosphere. It does not affect the thermodynamics of the planet. So this is what I call just biomass CO2. And that's why burning biomass is carbon dioxide neutral, because you're burning a plant that just absorbed the carbon dioxide from the atmosphere last year. Now, this equation changes, however, if the carbon is not completely oxidized, meaning if we're not just emitting carbon dioxide, but emitting, say, some methane or methane. Now, one way that can happen is if the waste is actually fermenting, because fermentation, the end reaction in fermentation, you get both methane and carbon dioxide produced in an equal mole ratio. And methane has a much higher global warming potential than carbon dioxide does. So we have to ensure that in the landfill that we are completely oxidizing the carbon. And that means we need to put vents down in the landfill and allow the methane to come up to the surface, and then we burn it or we capture it to burn it and make electricity. So we have to completely oxidize our carbon, otherwise the landfill will not be giving us zero carbon dioxide. There will be a significant equivalent carbon dioxide coming from the landfill. So let's look at, say, this case here where we don't completely oxidize the carbon. Let's say that your plant absorbed a ton of carbon. Well, that 1 ton carbon, of course, there's 44 grams of carbon dioxide for every 12 grams of carbon. So that works out to an absorption of 3.6 tons of CO2. So let's say this plant absorbed, or this tree absorbed 3.6 tons of carbon dioxide over its life. Then it gets all chopped up, taken to the landfill, dumped under the ground, and it ferments. Well, that ton of carbon is going to get evenly divided between the carbon dioxide molecules and the methane molecules, because it's a 1 to 1 to 1 ratio. So that 1 ton of carbon is going to lead to a half ton of carbon that's in CO2 and another half ton of carbon that's in CH4. Now, if you've got a half ton of carbon, then again, there's 44 grams of CO2 for every 12 grams of carbon. So that gives us 1.83 tons of carbon dioxide. So we absorbed, as this plant grew, 3.6 repeating tons. We're emitting 1.83 tons of carbon dioxide. What about the other half ton of carbon? Well, it ends up in methane. So we've got a half ton of carbon that's in a 16 gram molecule. So that works out to be 0.6 tons of methane. Now, the thing is that the methane has a much higher global warming potential than the carbon does. This has no global warming potential, or rather, it's just biomass because you absorb the 3.6, you're re-emitting the 1.83. But this stuff here, you multiply by 72, and then you find that this is equivalent to 48 tons of equivalent CO2. So because we did not completely oxidize the carbon, because we allowed some methane to escape, we absorbed over the course of this plant's life 3.6 tons of CO2. We are emitting 49.83. And clearly this is not carbon dioxide neutral. So we have to ensure that we are, if our waste is fermenting, that we are capturing this this methane, CH4, and not allowing it to reach the atmosphere. This is usually done by putting vent pipes down into the waste and then either burning the methane as it rises, or again capturing it with pipes and then pumping it over to a generator, and you can actually use it to make electricity. The Annacis Island sewage treatment plant does this, and there's a number of other landfills and wastewater plants around North America that are also using this as an energy source, which is good because it completely oxidizes the carbon, and it's also good because we get energy that would otherwise we can use that in place of, say, burning other fossil fuels. So that's a look at some of the issues associated with waste treatment. First, you've got the basic trucking and the energy and CO2 that that produces. Secondly, you've got the importance of properly handling the waste in terms of either making sure it doesn't ferment, or if it does ferment, making sure that you capture the CH4. Otherwise, you're going to end up with a large, significant impact on the atmosphere from the decomposition of the waste.